Hi, my name is Cameron Gordon and I'll be presenting a work on quantizing implicit neural representations. So what is an implicit neural representation? Simply put, it is a neural network that has been trained to learn one particular signal, which might be an image, it might be a neural radiance field, or it might be something else like a sound wave. In our work, we investigate compression of implicit neural representations. By incorporating an adaptive clustering strategy, we demonstrate improved performance at low bit rates. As an example of this, we compress neural radiance fields to 16 kilobytes, more than 300 times smaller than the original NeRF. We additionally explore the trade-offs between different architecture choices and quantization levels. Our paper builds on recent works which have explored compression of implicit neural representations across a wide variety of signal types and compression methods. So why cluster quantization? It helps improve data efficiency by better matching the quantization map to the weight distributions. And why adaptive quantization? Weight distributions typically change during training. Using the same map for each epoch will therefore introduce error. By periodically repartitioning, we can better balance the accuracy of the quantization with the computational cost. We find that periodically repartitioning helps reset the quantization error during quantization-aware training, leading to improved performance. Following training, we store network weights in an integer codebook and losslessly compress this using bzip2. Here we can see the difference for 3-bit training between a uniform quantization with fixed bounds, a non-uniform quantization with a fixed distribution, and one with periodic repartitioning. Periodic repartitioning adapts to changes in the underlying weight distribution. We compare our approach to a variety of quantization methods observed in the literature and demonstrate its applicability on a variety of image regression and neural radiance field compression tasks. What we find is that an adaptive cluster quantization strategy outperforms other quantization approaches at low bits per weight. At high bits per weight, there is a diminishing marginal return. We additionally demonstrate that multiple architectures and quantization levels can yield similar performance, with changes in the compressed memory. For neural radiance fields, we find that our approach consistently produces fewer artifacts when applying extreme quantization to 3 bits per weight. This enables compression to around 16 kilobytes, more than 300 times smaller than the original NeRF. Taking a closer look, we can note the lower distortion that occurs under this approach. Finally, we note that as different quantization levels and architectural choices can lead to similar performance, we can successfully train a binary neural network for image regression with a sufficiently large architecture. We note that as a large architecture is more memory intensive, it can instead be more memory efficient to use a higher level of quantization with a smaller network.